Cool, awesome. So yeah, let's start. Let's start with the coding problems. Like we will go through a couple of coding problems that, as it would be in the actual meta interview,
Yes, sure.
and like 10-15 minutes for feedback.
No problem.
Cool. Let me just press the first problem. Yeah. So basically, this is the problem. Like you have a linked list,
Mm-hmm.
and point in a critical point in linked list is defined as either local maxima or local minima. So local maxima is the node where the value of that node is like smaller than both of its previous and the next element,
Mm-hmm.
and local maxima, um, um, yeah, and the same like minima. So basically, you have to find out the minimum and the maximum distance between any two critical points in the linked list.
Okay. So
And
the minimum and the maximum distance between any two critical points in the linked list.
right.
Okay. So given a linked list head, return an array of length 2 containing min distance, where min distance is the minimum distance between any two distinct critical points. Max is the maximum distance between any two. If there are fewer than two critical points, okay, return -1, -1. Okay. Local strictly greater than the previous node. Okay. Strictly smaller. Can only be local if there is both a previous node and a next node. Oh, okay. I see. Um, so can the input so the input be an empty list here?
That's a good question. Yeah, it could be.
Okay. And okay, so I see from the example that not all the elements in the list would be distinct. Would be distinct. Uh, okay. And is there like any constraint on the length of the linked list?
You can assume that it would be 10 to the power 6.
Okay. 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 So I think when I think about so there is one maxima and then one minima, and we need to find the both of them, right? So because we are going to return both of the min, so we're going to find the min and the max distance. So I think this can be like as I think about it, it can be reduced to a problem where we need to find like or like we need to find each max and maxima and minima uh, maxima and minima in the list. If we can find it like through a scan, like all the maximas and minimas, then maybe there is a method like where we can keep track of the like the so that the early so if we get the earliest maxima and minima, and the one which comes from the so if we have the earliest maxima and minima and the one that is like nearest to the end, then we definitely we get the maxi distance there. Uh,
Okay.
that can be a maxi like that can be used to find the maximum distance between two critical points. Uh, so like once we start scanning it from the beginning and we notice there is a maxima or a minima like to a certain like at a certain node, we just note it down. And like but because it is a list, so we can't just scan the list from the end here. That is another point. So can't
Right.
just scan the list from the end. So yeah, so I think the method should be somewhat like include somewhat like scanning the list. Now let's see how can we scan. So first thing I notice here is that okay, we can have like a function which can tell like given a node, if it is not the first or the last node, we can check if that particular node is either a maxima or minima. We can just write a function, and that function would be like an order of one time. So we can check this for all the, for all the nodes. We can, like, from like the nodes between the first and the last node, because the first and the last can't be the critical points anyways. And that will take us order n time to check each of this node. Now, to check the nearest and the furthest, how can we basically do that? So in so I'm just thinking, is there a method we can just solve this whole problem in order n time? Like, I think one trivial way we can just, like, we can have the positions of all the critical points basically, which are either maxima or minima. We can store it in a, like, a array or something. Of course, that will take order n extra space. And then we can just maybe sort it out there. And when we sort it out, then the difference between the first and the last is the maximum distance for sure, and then we can just scan it to get the minimum distance. So but it will take, because there is sorting involved here, so it's so we this trivial method would take roughly, like, order n extra space, and order n log n overall time, because we are sorting it. Uh, but yeah, so this is just a trivial method. So now, like, just quickly thinking about what can we do, because
Need to
anyways,
sort? Do you need to sort?
what?
Do you need to sort this?
So yeah, I'm just thinking about, like, how can we avoid sorting. So here, so so if it is, so okay, so yeah, I think we do not need to actually sort, because we will, when we will be scanning, we'll just store it, like, store the critical point in the order, right? So
Yes.
there is no need to sort, and then we can scan it. So yeah,
Mm-hmm.
so as I said, like, there is yeah, this is actually not required. So
Yes.
yeah, so it is not required. So the time complexity will be order n, but the space, yeah, there will be extra space for sure uh, here.
Mm-hmm.
So just, like, thinking a minute about whether we would need this extra space, or can we do it in the space that, like order one space or something. Uh, so do you think we should think in that direction, or should we go
Yeah,
towards,
let's
like,
give a couple of minutes to that.
okay, okay. Uh, so here, let's store the first one, and when the next one comes, so if we store one critical point, we can store that one, the previous one. Yeah, we actually don't need to store it, because we can just actually compare, like, the distance. So the first one, we just store the first critical point, right? And we can compare it from the one next one that we get, and we should store the first one that we observe, the first critical point, and we should store the second one also, and we can keep updating the actually the difference, like, so we should keep updating the distance between the first and so the first one should be stored somewhere, and
Hmm?
thing is, the last one should be stored, and in the middle we can just keep an iterator for the point, like, between the current
And
and
when
the,
you say last, do you mean the last you encountered till now, or the last in the linked list?
so last year encountered till now.
Okay.
Yeah.
I think that would help. That would solve your problem.
So yeah,
Yeah,
so that
let's try, start with the code.
yeah, sure. So max, let's name the function some max min critical difference or something. Oh, sorry. And we have here a list, which we can say it's mm, anything like node, like a beginning of node of the list, and it is a list of int, sorry, and that we are returning is a Sorry, we are returning a list actually. So it's a list of max.
Yeah, so initially, uh, okay, what do you mean by okay?
Yeah.
Node is a variable, right? And the list of int, like, would will it be list of int or some structure or something?
Oh, sorry. Yeah. Oh, yeah. Sorry. So it will be a list node. Yeah. It's a structure. Yeah.
Okay.
And in the outside, we can have a array of length too, right? So yeah. So and here, so if so, we will first check like also like here there will be some cases where there is the list is empty, uh, if not a node or not node dot next. This means that if the list is of length, mm, yeah, so if the list is of length 0 or 1, so we have to return, I guess, -1 and -1 here. So we can return it here itself.
Yeah.
Yeah, so we can say edge cases here. Now we can just write a function def, like just to separate the logic here, the def if so so this head of the list will be node here, and we can check uh, with the beginning node with head of the list will be node here. So when we now know, so we can start from the yeah, so we can start from node dot next actually, yeah, here. uh, so what we need to check at each point, what will be the condition that we'll need to check, because we know there exists a previous node here, but there might not exist next node here. So and we need to continue till we keep encountering the node next to the head, because that means that we are still in the middle of the list. So while this, right? So this will be the like, yeah, the loop which will run n times. So this is, yeah. And now we need to check the condition. So is minimum, or like we can write two separate functions for that. So given a node, and uh, so we here we can write bool. Let's write this and the same as is maximum.
Mm-hmm.
Yeah. So yes, and also bool, and yeah. So first writing this function, but we don't have the, oh, what happened? Sorry. We don't have the, so when we get this node, we also need the previous value, right? So we should store the previous value, or like the previous node also here.
Mm-hmm.
Yeah, so that so here I have we can write this instead as a previous and current, or something. So uh, yeah, so yeah, so to name it better, just to name it better, we have previous as the node, and the current as node dot next. Now we are going to iterate while there is current dot next. While there is this, so we have previous and current, and we when we iterate, we can update these nodes. So anyway, so here we will have so so do we need to pass uh, all the, can we do it with, we just need to make sure, okay, if we pass previous in that function, we will only need to pass one element. Otherwise, we need to pass both the previous and the current node. So I think what will make the code cleaner is if we pass both, because it will make logic easier. So although we will be actually doing double the work, but I think yeah. So when we get this, we have if so previous dot value. Uh, is minimum, right? So is greater than, is strictly greater than dot current value, and current dot value and current dot next dot val is strictly greater than dot value. Sorry, we return true, otherwise we return false. Similarly here, if this dot value is less than, yeah, and so we return false. So now here, because we already defined our previous and current, and so what we can do is, if is minimum, so is minimum of previous and current, or is maximum. Okay, so should we check it differently? So this is the maximum, and okay, so it's either, the critical point is either maximum or minimum. So yes, so we have this. If this is the case, then we can store it, like, so we should store the first one for sure. So so how do we make sure this like, if when we encounter the first critical point, we store it in a separate, we store it just in a separate variable. So first we should like define the min distance we want to return, and we can define it as something like, because it's uh, so this is the min distance variable that we and so for just getting the min distance first, so if we have is minimum or is maximum, we can compare, so what was the previous distance, right? So we can define a previous distance as some like -1, because it can't be negative. So if we observe that the previous distance is -1, or uh, uh, if and we can also define the first critical point here as, say, -1. So if we observe that the if previous distance is equal to -1, uh, right? So that means we are still we still don't if this is the true, if the previous distance is -1, that means that we need to first input our first critical point here, right? Previous distance. No, the first could be, so if first we should check for this. Sorry, if first critical point equal to -1, so we should just add the first critical point. So where we are, we should also here current, what we should do here, because it's the first one we have already taken as previous, this is the second one. So the current, we can start from a 0, because at the end it's going to be the difference. So, and we increase this when we at the end of this loop. So first critical point is the current critical point, right? And so yeah if we get if else, if this is not the first critical point, it's the second one, and if the previous distance is, I mean, will it matter if we have the, yeah, if we have the previous distance as -1 or not, or we can just check the minimum here, because if it is first critical, we are taking it as else, so we can just check the current critical point minus. So the minimum we can just get as the minimum of the minimum distance and the uh, where's the minimum distance and the difference between the current critical point and the first critical point. Yeah. And we don't need to, I think, write this previous distance. So it's for either first, or like at the end of this loop, we can also check for the maximum by okay. So the so we are increasing the iterator. We can't say it was a critical point or not. So I think this should, like, this should be called an iterator. uh, yeah, iterate node current ITR, right? And um, so this is, if it was a critical point, it's this. Uh, at the end, because we are not storing it, the current critical point anywhere, so we can just say, okay, last critical point. Yeah, we should store the last critical point somewhere. So yeah, it should be called an iterator. It shouldn't be called a current critical point, because we are storing all the points here. So okay, so just a time check. I don't think we have much time here. Current iterator is 0, current iterator plus equal to 1, and here it should be current iterator instead of critical point. So that means that it was a critical point, and that's the, so the last critical point, where will it be stored? So the min distance, we got the min distance, max distance, we got the max distance as we can say -1, and we can just
Mhm.
do a max distance here also, although it will calculate it again and again. But for the last time this loop is run, the max distance will automatically get updated. We, instead of the okay, so this here, when we do max distance, why we are doing it with the first critical point? It should be the previous one,
The
right?
max should be with the first, right?
Yeah, max
Max
should be
will
with,
always be between the first and the last.
yeah. So this
So
is the max.
last would
The
be
min should be with the
always.
so min should be, so else. Oh yeah. So that's why the previous distance was important, because if the previous distance equal -1, both, so the min distance was supposed to be this, right? Else it was supposed to be and we can just previous is equal to
What do you mean
previous.
by previous distance?
So it is the, like, the, if we are updating, if it is the first time that when we reach the second critical point, right? So the minimum will
Mhm.
be this, right?
Okay, the
And
distance between two consecutive critical points.
yeah, two consecutive critical points. So yeah, previous distance is distance between two consecutive critical points. And so we first time we do this, and we assign the previous distance as this, right? So here, so when we decide the previous distance as this, so we what we can do, how, so the thing is, I'm not
Even
storing
previous
the,
distance, like, do you
uh,
need previous distance? I'm not sure.
okay, just uh, yeah, I think you're right. Like, you can just simplify it here somehow.
Right? You can just look like, because if the first one is not initialized,
Mm-hmm.
then there is no previous distance calculated, right?
Yeah, yeah.
Um, so you can I Like, and your infinity takes care of running this minimum condition anyway.
This minimum
So
distance is, yeah. So here, I'm just saying that instead of this first critical point, I should be doing the distance between the current iterator and what the previous critical point was, right?
critical
And
point, right? Distance, right?
uh-huh,
Yeah, yeah. Current and the previous critical point, not the previous distance.
yeah, yeah. So I'm not storing the previous critical point anywhere in this code, right?
Right.
Yeah, yeah, yeah. So the first critical point and the, sorry, and the previous
Last critical point. Okay, yeah. Previous critical point.
critical point. If
You
point.
can assign, you can initialize it in the first if condition, right? So whenever you are initializing the first critical point, you
Mhm.
can initialize to be uh, previous also, right?
But then the condition is if first is -1. I should initialize it in every loop, right? Not only when the first critical point is -1. Yeah,
Okay.
yeah. So I'm just like here else, like if previous critical point. Yeah, I can assign it here. First is,
But it should not be only in else also, right? It should be both. So it should be out of like this if block.
yeah. So if uh, out of this, so is what is this previous critical point? If it's if this is -1.
Either way, right? Whether it is -1 or not, you will still need to update it.
Yeah, yeah. So yeah, sure. Thank you. This will go here. This will go here, and then we can at the end we can just return a list of min distance and to I think do we have time for this problem to go over the tests or
Do you need to check whether the if previous critical point is not -1 while calculating the minimum distance?
yeah the first time.
Okay, yeah, but you won't go for the first. Okay, sure. I think yeah, that would be handled. No worry. Sorry,
Um,
my bad. Yeah. I think yeah, this should work. Let's move to the second question.
yeah.
Yeah. So the second question is this: like you have, I'm pasting it at top.
Okay.
So you have two nodes in a binary tree. You have to find the lowest common ancestor of those two nodes.
Okay. So lowest common ancestor. Uh, so I think lowest common ancestor. So it's going to be the, so if we go from the node, and these two nodes can be anywhere in the tree, right? Yeah.
That's correct.
Okay, two nodes anywhere in the tree. Cool. So I think because we are talking about ancestors, so one thing that could definitely help us here is if like we can just traverse the tree, and while traversing the tree, we can also mark down every node's parents, right? Um, and when we mark the parents of the each of this node while traversing the tree, we can then we can just start from, like, we know like what are the what are all the nodes that one would encounter from going from like one of the node to the root, right? We have that path, and once we have that whole path, we can store that path in a set, right? And then from the second node, if we start to iterate it, we can start to iterate. We when we like encounter the first node that was in the set, in the previously mentioned set, where we already have a path from the node 1 to root, then that node would be the lowest common ancestor between both these two nodes. So however, like in this case, because so what we are essentially doing, that are we are storing, we are basically we will be we iterate in a manner, we store the apart from the left and the right child, we want to store the parent of each node, which means that it will cost us order of n space for each node in the tree.
Okay.
Second, we also plan to store store the path store the path from the like from first node to root.
Mhm.
And so this path, because like maximum it will be the height of the tree. In worst case it will be order n, like in an average case it, because the height is log n, so we will be like spending this much space to store that. And in the next we don't need to store anything, because we will be just checking the parent of the, like we will be just checking from the second node which is the earliest parent, which is in the set. So this will be stored in a set. So overall, I think in terms of time, like time complexity, in terms of space complexity, it will be order like n plus and n, like here, like for the two steps in the worst case. So it will be order n space we will be spending
Mhm.
for the problem. And like apart from this, for time, because we are doing a traversal first, which will be like can be any traversal, DFS or BFS, to store it. uh, for that it will be order of n time. And then like for going for the while constructing the set, it can be another order n time in worst case. So yeah, so it will be
Let's start with the code. I think, yeah. It would be
okay.
linear in space and time both, right?
What?
Your approach is linear in space and linear in time, right?
Yes, yes. Yeah.
Okay.
Okay. So yeah, we can go through the code also. This is like lowest. So here we have uh, like say we have a tree first. I'm assuming the tree node has like value left and right here. As
Mm-hmm.
it we have like say node A here, which is also in itself a tree node, and we have a node B, and we have to return another. So in this case, we have so first we need to build. So how can we build the parent? Uh, so first we just take the, like we just mark the head as root, and we can have so for doing the breadth first search, where we'll have we'll have the head, like the parent node, and we traverse to its left and right children. For each of them, while we traverse, we just make sure that we create a dictionary in which for each of these two nodes we mark like for the keys of the dictionary will be the child nodes, and the parent node will be the value. so that when when we are creating the set, we have this dictionary at hand. So we can have this as a child to parent dictionary here. And because we are starting from root, so we can that. So I am doing here BFS, so I will be implementing it using a queue here. So we have a BFS queue, which will be just um, in in Python it's DQ, right?
Mm-hmm.
And so what we do is we just push in the queue, the push in the queue the head node, right? And while there so here how to check if it is while CFS. So if it is empty, is it is empty, or I think there is a function, but we can check is while if this queue is empty, I think it returns none. So we can just check it like this while BFS queue, like if there is something in the queue, right? Um, so
Mm-hmm.
what we have is so if like so we will get the the current node here by using this. So this will be BFS queue dot pop left. Right? If there is a left child to this node, what we can do is we can add child to parent dict left this as the current node. And if so, similarly we are doing it for the right. And once we do this, so this we also need to like if there is, so we are adding it to the dictionary, but we also need to add this particular, so bfsq dot push uh, push the left node here. And so similarly we can push the right node here. So this will end, so this will take, because we are iterating over of the each of the node in the tree till like queue is empty, and the queue will be empty when it is like nothing to push here. So when all the leaves, like we have reached all the leaves, so we have this order and time. Now we need
Sure.
to, yeah. So now we need to like make, so we have node A and node B, and we have this dictionary which is constructed. So what we can do is we can construct like a set, like we can set path node A to root. This is a set. And what we can do is while um, so how will we construct this set? So we have while uh, node A, and because we already stored we already have this root root here. So while uh, node A not equal to so what we can do, where should we end this loop while? So because we are okay, so let's check like we can check an iterator from node A. We can check there's a node A, right? Another. So while this iterator doesn't have a parent, right? Like so node is going to be the first node which doesn't have a parent. So we can
Yeah.
just
Just time check. Like we have 5 more minutes.
5 more minutes. Okay. So while
Five.
yeah, yeah. while iterator of node A, um, where is the dictionary child to parent dict? Node A, yeah. So this is not there. What we can do is we add reach to the iterator. A. This will create a path. So from A, so now similarly, while we make another for node B, while B, um, uh, iterator node B. So we iterator node B. If not, we can check. Can update it as iterator node B. Else, like if there, I think there is guaranteed to be a, like I'm assuming there is guaranteed to be a lowest common ancestor, or it will be root because the root will be included here. So if we reach the root, it will return the root at the end. Yeah,
Right.
yeah. So should we go through some cases, or do you think there is time for feedback now? Or
No, yeah, you can identify like few cases. Like don't need to run through, but you can just verbally talk about like what are the good
I
test cases.
I think for me, I would test it for sure. Like some of the edge cases, I would be
Mm-hmm.
testing it is when the tree is like in a straight line. So when one of the node is ancestor of another node itself, uh,
Mm-hmm.
is ancestor of another. Another test case I will test is when uh, when one like okay, like I think one other interesting test case is when both nodes are same. uh,
Mm-hmm.
and another test case is when both the nodes are in different, like the left and right subtree of root. Uh, yeah. Another test case I will definitely check is when tree is empty.
Mm-hmm.
Another like test case is when one of the node is null. I don't think we clarified it earlier, but it could happen that one of the node is itself null or something, right? So it is not in the tree, right? So it should return it. So definitely, like if that is the test case, if one of the node is null, we need to figure it out before itself in our code, rather than just going through like all the code. What should be the output? And I think here there is no LCA, but we didn't discuss this case like earlier in the clarification. But definitely, uh, another like test like edge case like could be like because we build upon this in future and something. So it's just like like a node with just a left and right subtree and different cases within that, right? So maybe just check the root and the left, root and the right, and left and the right, and check if this basic test case is working or not. Yeah.
Cool. I think yeah, those are really good test cases.
Yeah.
Let's pause for the feedback, right? I think like yeah. So I really like the way you clarified for the first problem if list could be empty.
Mhm.
You also shared the observation that there are duplicates in the given example,
Mhm.
and you asked if like there is a limit on size of linked list. So those are really good clarification question you ask like before jumping into the solution.
Mhm.
I think like you mentioned that if you can find all local minima and local maxima, you can compute the answer. That was good
Mhm.
observation.
Mhm.
Then you mentioned that maximum distance would be between first critical point and the last critical point.
Mhm.
And the next observation you shared was like as it's a linked list, we cannot scan from the end.
Mhm.
So yeah, I really like the way you communicated your thoughts clearly rather than just like thinking in silos.
Mhm.
I think like you mentioned that you can solve in linear time by storing the position of all critical points in with additional space of linear of order of
Mhm.
n. I think like, you got confused like that you would require to sort this list.
Mhm.
But yeah, when asked, like you identify that sorting is not required, and you
Mhm.
correctly analyze the time and space complexity of your first solution as linear.
Mhm.
And I think like you took a pause. That is one good thing you did. Like you took a pause and asked like whether you should really try to optimize for space complexity,
Mhm.
because that is a good thing. Like rather than wasting time,
Mhm.
um, yeah. So asking interviewer is a good strategy always.
Mhm.
Then you mentioned that whether you need to store the first, that you will need to store the first and last position of critical point,
Mhm.
and yeah, and you can optimize the space complexity to be constant.
Mhm.
And yeah, I think you came up with like correct method signature. You use the optional to efficiently deal with nulls,
Mhm.
and like yeah, you identified the edge cases that if the list is empty or a single node, and you wrote those edge case at the beginning,
Mhm.
and then you try to write a modular code with like having local minima and local maxima check as a separate helper method. I think like you needed some help on implementation details, but that's okay. Uh,
Mhm.
yeah, and like you were able to complete the implementation for the first problem. I think like you took much more time. Like it was like close to 30 minutes when you were done with the first problem.
Mhm.
But yeah, you cover up the time by implementing the second problem faster.
Mhm.
You clarified like whether two inputs nodes can be anywhere in a tree. You
Mhm.
shared the approach where you will update the parent pointers for each node and linear path and then find the path from given node to root.
Mhm.
Um, I think like you did well by correctly analyzing space and time complexity.
Mhm.
And yeah, um, I think like the way you explained was also good. Like you went through each step of your approach and explained like how much time it would take in this particular step,
Mhm.
right?
Mhm.
I think like you were done with the code within given time frame, and like you were able to come up with like really good test cases for the second problem,
Mhm.
right? But as like we didn't have much time, we could not discuss about optimizing your approach for the second problem, right?
Yeah. Yeah.
But I think that's okay. It wouldn't be optimizing like asymptotically. It would be just like if you can reduce the passes we are doing through going through the tree.
Mhm.
But yeah, I think it's acceptable solution. But yeah, I do feel like when it comes to pointers and maintaining like different variables, I think you do need some practice. Like it, like at least like the first problem could have been solved like at least 5 6 minutes earlier.
Mhm.
Uh, yeah, so that is the only area you should try to improve. Like try to practice with few more questions involving pointers and arrays, so that
Mhm.
like yeah, the implementation things get clear.
Yeah.
I think yeah, based on this interview, it would have been higher call. There is no issue in that. Yeah, and the highlight of this entire interview is your communication. I think
Mhm.
that's the biggest positive from
Mhm.
this interview. And another good positive is like your code quality. You
Mhm.
are able to code in like in for one go without having much like many bugs in the implementation, handling the edge cases. So yeah.
Yeah. Yeah, yeah. So is there like, because I have my phone screen this week for Meta, do you think
Okay.
like, because yeah, so I
Oh,
think one I have been
yeah.
striving.
Hopefully would be even easier than this. I think questions would be easier than this.
Okay. Yeah, so I was just thinking about it that, like, I need more time for the on-site. Definitely, I feel that in terms of my time management, because
Mm-hmm.
sometimes that, I take more time than is required. I can solve
Right.
the problem, but yeah, so I'm trying to do more, like, the timed contests or something like solving two problems in 40 minutes kind of, challenges.
Mhm.
But I do feel I'm okay to go for the phone screen at least this week. So let's see how it
Right.
goes.
The only hint would be like in Meta, your coding interview don't have any out like any say on your leveling part. Like it just say that whether you have decent coding skill for Meta or not. It does
Yeah,
not have any right about deciding your level. It's just system design and behavioral which decides the leveling part, right?
yeah, yeah.
So it's okay to be abstract while communicating your idea. Like it's okay to skip some steps while explaining your like for example complexity analysis. It's okay like say that like okay like maximum the bottleneck is like going through all the nodes. It would be linear, and also
Mm,
we need to store it. It would be linear. And then like,
mm.
yeah, so if you can, it's okay to be abstract at least in Meta while explaining your approach. Yeah, because like it's really important to get two code complete. Like yeah, there is unlike Google or Amazon in Meta, it's compulsory to have two code questions coded.
Yes, yes. Yeah, I do understand, like, know that. Yeah. Um, uh,
Okay,
so,
cool. I think for phone screen, I think you are sorted.
mhm.
All the best for your phone screen. And yeah, and like maybe if you require, like you can reach out to me or email if you need any guidance regarding system design or behavioral interview. So yeah.
Yeah, sure. Sure. Thank you very much. Yeah, definitely. This was very helpful, and yeah, I hope to speak to you sometime. Yeah.
Cool. Awesome. Awesome. So are you applying for London location or US?
So currently I am in US and I'm applying for US locations.
Okay. Sure.
Yeah.
Cool. All the best.
Yeah. Thank you. Okay.
Yeah.
Bye.